Okay. Welcome to today. Before when it's over, when class is over. Okay, so the last time, we introduced this notion of Dedekind domain. I sort of flirted around with what the idea was before, but it's basically in the theory proof of domain. So let me recall that. So a proof of domain, one of the equivalent conditions was every finite generated ideal is invertible. D, if you're in the theory proof of domain, the theory means every is finite generated. So every ideal is invertible. Here's the last theorem. If you had stated only last time. 5, 2. Follow your equipment. 1. Predicate or every non-zero ideal is invertible. D is one-dimensional. Integral closed. And theory. Three. B Noetherian. And for all P, inspect B. R P is a evaluation domain. I put the theory in parentheses here because if you assume the theory in the first place, then the DP is still in the theory. And 4, every non-zero ideal is uniquely a product of prime. And one might consider this one kind of a very sort of utilitarian characterization. And I'll explain that in a bit. Let's go through some of this. I am going to prove. I'm going to prove the equivalence of these. And I'm going to sketch. I want you to think about this one. I want to sketch both directions of this, how you might approach it. Student 1 implies 2. Okay. Every yes.
Yeah, first off, last time you wrote dimensions less than or equal to 1, so it doesn't have to, can't be 0 or not.
Oh, yes. But let me follow. Your question with a question. What happens if it is 0 dimensional? You don't have to go too far afield to find the answer. What's a 0 dimensional domain? It's a field, right? So there are actually some authors that ignore the 0 dimensional Dedekind. Say field is not a Dedekind domain. I consider these people wrong. But yeah, so I would say But we'll focus in our proof, we'll focus on the one dimensional case because the proof of zero dimensional produces nothingness usually. Okay. One implies two. We know D is Dedekind. And we'll soon have a field. So every non-zero ideal under a proper ideal is invertible. So ideals are invert all five. So the got so how about the other stuff? Um Now, pick your favorite maximal ideal here. Alright. Notice that if we look at the localized M. Fires. Well, if you look at delocalized at M, what do you know about the max deal?
So, theory evaluation.
Okay, well, okay. What we have, we're under the substance D is Dedekind. What do we know about M? Well, right, but it's inverted, right? M is invertible. So when I lift him up to that localization, it's still an invertible ideal. And so since you're in a local ring, it has to be principal. Right? So DM is a focal PID. So it is an inferior calculation. In particular, if this were a field, of course, it would be dimension. But we could assume the dimension of DM is one. And here, of course, MDM is principal if it was not the sequel. Well, no, MDM is principal. Let me be careful. M is invertible if it's not zero ID. And if it is zero, it's still principal. So. Right. This is by the correspondence theorem. Because if P taken in, then P M D. There we go. Then P D is contained in here, which means it's a zero. Right. Okay, so we've got this. So we've got, Ethereum is, one dimensional. How about interval closed? Atlas. Remember, any valuation domain is interval closed. So delocalize it in as interval closed.
Oh, but T is the intersection
There you go.
of all.
Good. We have a theorem that says, if you have a family of closed domains, it's intersections. So there you go. So we got it all. It's amazing what invertible ideals get, right? Okay, let's do the next implication. Of course, in the implication 2 implies 3, we get the theorem. Right, problem there. Now, suppose. So we need to show DM is, in the theorem. Now this is kind of fun. Suppose not. Then there exists, such that, DM is, not in the theory evaluation. But let me note at the outset, what do we know about DM? Right. Of course, I use the word local, just theory. Let me make clear, we know for sure it's local, the theory, and what else? I will again discard the case where the dimension is 0, because then it's a field. Right. So we've got all that in for us. And we're actually, the dimension 1 business is gonna be important here. So. We. All right, so I'm gonna just shorthand my notation by DMR, and instead of writing MD, I'll write M to be the maximum ideal of this local ring. Let's suppose M. Yeah, I mean, that's because if you have, if this is the only prime ideal, it's not zero, it's principal, then you have a PID, which is what we want, it's an evaluation. So let's X be a non-zero, non-unit element of M. Let X. M. X. M. So X is not zero, it's a unit. This is an important observation. That's kind of cool. Arbitrary element. The maximum. Can somebody explain why? That is right. The radical of X is the intersection of all prime ideals contained in that element. Guess what? There's only one, right? So there you have it. What does that mean? That means if you pick any element in M, then some power of it is divisible by X, right? So in particular, let's look at the generators. Let's see. Right. So there's a power of this guy, it's in like that, so it's on, just take M to be the maximum, all these powers. That's again, this is kind of the fact that this is finally generated this bill here. And it's really why you need an Ethereum assumption here. Now I'm gonna pick the special element. I'm gonna let Y. So this is the product of all these generators to one less. Now, what's special about Y is that if you hit anything in M by it, uh, right, because anything in M is a linear combination of the AIs. And so that's set up to get you that what? Uh, so if you hit it by any of these Ys, then we distribute it, the first factor, A1 has M powers, now A2 has M powers and so forth, so everything's in A's. So we have that going on here. Let me also, wild X is in M inverse. right? Because if you hit wild Rex times anything's visible by X, knocking it back into the ring. Right? So, like. Okay. Everybody with me, so. If. Oops. If NY is exactly equal to principal ideal, that means the M is generated by X over Y and principal. And you're done, because now you have R is a local theory ring, its maximum ideal is generated by a single element. It's principal, so it's a local. So it's a theory. You okay with that, Charlie? You look disturbed.
Why can you divide by one?
Well, so this is an idea contain. If we know that wild roots is in inverse, right? So. Think of it this way, I've already got this contained. We've already got this contained, right? All we need is anything X over Y is contained in it, right? But if your assumption here is M times Y equals X, then take.
Oh,
Right, and M is. Right. So, is everybody cool with the fact we're done if we have equality? So we can assume that this containment is strict. So. And so M inverse strictly contains R. Let me point out that M inverse softly contains R, right? Because for example, everything in R times everything, everything in R times everything in M is still an R, because M is a proper identity of R. So M inverse has to contain R. But it also, by the fact that this is strict, it must strictly contain R. So.
So why does that apply to strict containment?
Uh. All right, so let me try to explain this better. That's okay, right? Uh. If. if it doesn't strictly contain. So not strictly contain R. If it doesn't strictly contain R, then M inverse equals R. Correct. Which means, that Y wins. And so that means Y is not X. Uh,
So I think what we should do is instead of taking local M for each I, sorry. You should take, M sub I, to be minimal for each AI, which means that then this Y we construct is not an element of.
I'm not sure that's gonna cut it. Cause that, some factors don't agree with. That's gonna become the problem.
Sorry, but what's gonna be a problem?
So what you wanna do is take different ones that are minimal, right? So this is small one that you has. But then, so you take this Y and you divide it by X, right? It's got these other factors contributing to it. So just because, for example, A1, A2 just by themselves could be in the ideal zone by X. But without the need of exponents, right? Should be able to be done this way. Let me see if I can something here.
I mean, I believe you, but I don't understand what you're just saying, because like, at worst case, MI would be one, right? So then. You're just taking power zero.
Let's see, what do we know here? What are we doing? 2 plus 3, but. So let's come back to this detail. Well, let's take this back down and we'll come back to this. Let me finish the idea here. So, so in verse. So if this, actually, it doesn't matter if it's, we must have this contained anyway. We know that actually, we may not need this detail. No. Okay, certainly this is true, right? Because M inverse is at least R any, whether it's strict or not. Right? And certainly R times M contains M. And if it's bigger, that's more valid. If equality holds. If equality holds, anybody tell me what this says?
Yeah.
Right, because M is fine. So take an arbitrary lambda in, there's your module. Lambda times M is contained in M. Alright. Everybody okay with that? So anything in M inverse times M is still the finite generated module M. So that means that every element of M inverse is integral overall. Alright. Y'all remember the characterization of integrality? It's integral if you can find a finite generated module M such that U is contained in M. Well, that's what you got here. If you have this equality here, anytime you hit M with something from M inverse, it's still in the finite generated module. This means that every element of M inverse is integral over R. But what do we know about R? R is interconfluence. And so is its localization. And this is what it's true. It's contradicts. So, since we've contradicted that strict containment, what do we get? So. Therefore. M. And so principal. Have or. What? Who knows?
I have a question. Why is R a subset of M inverse?
Well, that's the detail. All right. Everybody follow module of that detail? Right. Okay. Everybody, okay. You have the script, we're good, right? Just don't necessarily have the script yet. So. Actually. Right. Yeah, so let me get back to, let me finish up three of them. He is Ethereum. He is Ethereum, and for every prime ideal, deal plus these Ethereum backbase domain, we show these. That is, we want to show that, every ideal, every non-zero ideal. So. Last one. Um. Let I. And he. We. Uh. Let him be. Uh. Let him be any minus one ideal, then. Uh. Well, is. Principal. Because again, any of theory violation is, a local PI. So, in is principal. In. I'm gonna check, I'm using. So what does that mean? I'm being tricky. I need one more thing. I know that I localized it in is always principal. But what I'm going for is size of vertical, right? I need one more thing. The theory. I. That's fine. And then local principal. So I. Okay. That module, that one thing, still, that wraps up equivalents of 1, 2, and 3. So I'm going to, I promised, I'm gonna show you, I'm gonna link 4 of these. I'm gonna use these 3 interchangeably as needed because I shouldn't. Suppose I have a dedicated domain. Why is it true that every ideal is the product of prime ideals? Not. Somebody describe the process. I can describe this pretty much. How is it that I can express I as a product of prime ideals?
So like.
Right, but, well, so let me rephrase the question. If this is true, I have to be able to write I as a product of some prime ideals. What suspects do you line up? Let me give you a hint. What's the easiest case in the world? How could I have made this, how could I have selected how to make this really easy? I as a prime itself. What if it's not? It's contained in. Right. What if not? That's actually something you prove on those. So I inverse is bigger than P1, right? And so now consider P1 inverse. P1 inverse knocks I somewhere inside, somewhere inside. That's right. So you continue this process. So what do we get out of all this? Well, we get the following. We get the following chain. Prove about the chain of ideas. Stabilizes because dedicated domains are nothing. Right? And so at some point.
How do we know what sunrise we should be?
What's that now?
How can we know that when the change in sunrise is exactly in the?
Well, because if it's not, then it's in some other idea, and you keep it going.
Oh.
Right. Okay, how about the other direction? What, one way to do this is to localize. Let me point out. And every non-zero ideal. Proper ideals, product primes. To show it's dedicated. It suffices to show. That every non-zero prime ideal is invertible. Because since every ideal is a product of these primes, every ideal will be invertible. You might think about localizing this. And we'll talk about this later. I will plug the hole on the inverse next time, strict containment. We'll get to that, next time. And if you beat the punch, you will start.